what we did last time, we defined the expected value, which is nothing but the weighted average of all those possible values taken by random variable x, and those weights are nothing but the probabilities. So if variable x takes on small x1 through small xn, there must be each corresponding probability for each outcome. So first probability should be this probability of x equals x1, and all the way to the last case, when x takes on the last value of x little n. You just come up with those products, weighted version of those possible values of x, and then add them all up. And that's what we define as expected value, or simply expectation. What it does is just basically let us know where the center value of certain distribution is. And then we try 3 examples. First, when we supposed to roll a fair die, we want to forecast its outcome based on its expected value. It's just nothing but the same probability of each occurrence, which is 1 over 6. And you just multiply that one by those potential outcomes and add them all up, and you get 7 over 2. And second example concerning those 3 different buses with different students, numbers of students in it. And randomly pick one guy out of those class size of 120. And then when you define x to be the number of students on the specific bus of the chosen student, what is the expected value? You just come up with those probability first of the random pick. So first case, the student is drawn from the first bus. And second case, where it's randomly picked out of the second one, and then the probability for the last one, and you can just easily compute those expected value as well. One of the important things that we did last time was this proposition. Something important, but not as important as theorems, but we still need to prove it. We just basically skip the proof in this case. So the reason why this statement, proposition, is especially useful is because of many reasons. First one is that you don't actually have to compute the probability mass function of some complicated function of the original x. To say that there's some real value function little g of the original big X. So if you just strictly follow the definition of the expected value, you not only have to figure out the function value of this g of x thing, also need to figure out this probability mass function of this g of x. So be careful that this P, not the PMF of x, that's the PMF of this g of x. But in this case, that can be replaced by the probability mass function of x itself. That's the power of this proposition. So if you stick with the original definition of this left-hand side, you have to sum up all possible products of those realized value, g of x, and then PMF of g of x, but this one nicely and conveniently replaced by the original PMF of x itself. So the burden is a lot more light compared to the case that we actually had to go for that PMF of g of x first and then compute this mean. So as an application, we tried this example. When you define second variable based on this original x, and y can be defined as x squared, while we are only given the PMF of the original x, not the PMF of the transformed x, which is x squared in this case. But if you simply apply the proposition that we just introduced, you just figure out what are those possible values taken up by this x. That's only 1 and 0 in this case, because original x takes on either -1, 0, or 1, and those 3 possibilities, the values in terms of this x squared is nothing but just a 0 and 1. So just figure out each corresponding probability, and you can easily compute the expectation of this x squared using this proposition. Otherwise, you first have to derive the PMF of this y, which is x squared. So everything is two-step-wise. But if you use this proposition, it just can be done immediately, directly, doing by only one step. So we stop there. As an extension, further application of the introduced proposition, we can easily see that this is the case. So what's going on is first come up with some random variable x. You transform it through some sort of like linear transformation. So linear transformation is nothing but you first multiply the original x by some constant b, and then add up by another constant b, which is different from the first constant. And then this corollary states that the expectation of the linear transformation of x, which is this a plus b times x, can be obtained by doing the linear combination of the expectation of x, not x. So that's saying a plus b times expectation of x. Does anybody know what the corollary means? We introduced this proposition, something like theorem, but not as important as theorems, but we still need to prove it. But there's also what's called a corollary. What's corollary? If you have taken a course in mathematical analysis, must have seen this word before. It's still important, but you don't have to prove it. Just a direct application of this proposition. So one of the important but useful proposition of this application of this proposition is this corollary. So how do you show it? If you have to, somebody asks you to show this. Intuitively, it's very clear. Take the expectation of some transformation of x. It says that that's nothing but the transformation of the expectation of x, not the original x. But if I ask you to show it, how would you? We'll start from the definition. What else? Got this, right? So left hand side is expectation of the linear transformation of x. So that's e of a plus b times of x. B times x, not b times of x. So by definition, across all possible x, right? That's how we define the expectation of something. The same thing, you multiply it by its probability mass function, and then sum it over all possible values taken up by this x. Well, actually not. This first should be the P of G. But then it can be eventually replaced by x by that proposition. What I'm saying. So if you just strictly follow the definition, the probability mass function located here is actually the probability mass function of the entire thing. But because of the proposition, you can replace this PMF by PMF of x. So that's actually because of that proposition. So let me repeat it. If you just follow the definition, the weights assigned to this each value of this function is actually PMF of this function. But because of that proposition that we introduced, to the page back, this proposition, and you can actually put the PMF of x here, not the PMF of that function. So where would you go now, if you have this? How do you lead to the corollary from here? I want to show this. So that's nothing but that. So how do you do it? Anyone? Expand it. Just expand the summation. It's a distributive property, nothing more. Right. Just apply this PMF to the first factor inside the bracket, and then do the same thing for the rest of them, and then just break it into two parts. Now what? seems to be quite low. Should be a good time to check the attendance, I think. I borrow a blank sheet of paper from someone. Oh, I got it. Thank you. So where would you go now? Pay attention to the fact that little a and little b are constants, so you can easily pull it out because it's completely free of that index. So if you pull the little a outside, p of x, little x. And if you do the same thing for the second coefficient, that's little b. This. What is this? Why? Because it's a PMF. Yeah, exactly. So that's one because of its PMF. What about that? That's U of x, yeah, exactly. By definition. So you're done. Okay? Quite simply done. So that's how you show it. That's the expectation. Keep in mind the definition. It's useful property, especially the proposition. If you have to compute the expectation of some real value function of the original x, you still can rely on that original PMF of x. You don't have to bother to derive or compute the PMF of the function of that x thing. It will save your life on many occasions, including a quiz and exam. Last agenda in this chapter is a variance, which is another very important notion about the population. So it basically measures how much spread, variation we might have in certain probability distribution. So first is first, a mathematical definition is this one. You first have to figure out the expectation first. So introduce some random variable x and define its mean, expectation of it, u of x thing that we have been discussing so far. Use notation mu. That's a Greek letter. People read it as mu. So you write it as a mu and read it as mu. So that's the usual notation for mean of certain thing. And be more specific by putting the subscript x, but sometimes it's little. So if you see mu in this class, that typically refers to the population mean of certain variable, E of x. So definition of variance of certain thing, certain random process or random variable, you take the expectation, and what is being taken the expectation by is just this one. X minus its mean first, square it, and then you take the expectation of that thing again. So there's expectation twice. First put the expectation of x itself, and then you take the expectation of the entire thing, which is the second expectation. So that's what we define as variance. So if you're confused by that new notation, think of it as the following. So variance of x defined as expectation, and that expectation is so in this handout, the E of x, inner E of x is replaced by this simple version, u. Compare this one with its sample counterpart that we introduced in the very first week. So since this quantity is usually not observed, you estimate it by sample variance. You see the resemblance between the population quantity and sample quantity. So this is not known to us, so you estimate this one by this. Sometimes you subtract 1 at the denominator of this fraction, but other times you just simply divide it by n. Mostly the same, especially given the large sample. What happens if you forget this exponent? So if you drop that 2 thing, what you're having is the following. Right? What is this quantity equal to? The 2. Shouldn't forget to put 2 there, but for some reason if you forget it, what the whole thing becomes? Expectation x first, subtract that from the original x, and then take the expectation whole thing again. What's that? Remember the same thing for the sample counterpart? We did something like that in the first week too. So that's a population concept. But if you come up with a sample counterpart, that's this. What was the value for this? 0. So what's the value for this? 0 as well. So that's 0. And that's also 0. The reason why it's 0, you can apply the expectation to each factor inside the bracket, just like the summation thing. Right? So there are 2 terms inside this big bracket. First apply this operation to the first term inside, and then apply the same operation to the rest of it. You get this. But this one, you took the expectation of x first, and then took the expectation of the entire thing. So taking it twice doesn't make any difference. You first take it, and that's it. So you once take the expectation of certain thing, whether you take it again or not, it's still the same. So that's the same as u of x. Because once you take the expectation of some random variable, that becomes some constant, and expectation of certain constant is just the same number. So for example, expectation of number 5, that's just a 5. Because there's no randomness, it's just a fixed one number. So whether you look at from here or there, it's the same number, so it doesn't really change anything. So it's just a 5. So e of x is some number, since you wiped up that uncertainty by taking the expectation. Taking that expectation again on that fixed number, it's not going to make any difference, just the still same number. So that's a e of x. So you're basically subtracting certain quantity from the exact same thing. So necessarily the answer is 0. So there's some interesting analogy between expectation and variance, and then there's sample counterparts. So if it's the mean or expectation, sample version of that is the sample mean. If it's a variance, sample version of that is the sample variance. And similarly, you can show that there's an interesting analogy between expectation of the deviation of x from its population mean and deviation of its sample point from its sample mean, not expectation. So that's variance. Based on that, we can easily define what's called the standard deviation. Most have heard of it. The population version of the sample standard deviation that we introduced a few years back. Simply take the square root of this defined variance. So if you take the square root of it, people call that as a standard deviation of x. Okay, 2 definitions. Very important. What's the point of taking the standard deviation? I mean, once you define this variance, why don't you just stick with it? Why do you have to define the so-called standard deviation? Because these are essentially the same information. First, to compute this one, whether you take the square root of it or not, it's the same sort of information, but sometimes this one can be useful. What's some of those reasons why we have to bother to take the square root of it? One of the reasons was units are the same. Unit of x and unit of the standard deviation is the same, because here original unit of x, whatever that is, you have to square it. So the unit of variance of that thing is going to be not the same as the unit of the original x, but since you take the square root of it, the squared unit becomes unit itself. So the unit of standard deviation becomes the exact same as that of the original x. So one of the reasons. And second reasons, there's some other technical reasons why people prefer to use this second measure to the first measure, but it's somewhat awkward to introduce those reasons at the moment. So you just think of it like one of the reasons is because those units are the same. The unit of x happens to be identical to that of the standard deviation of x. So with these definitions in mind, we try some interesting facts and then relating examples, of course. One of the very important ramification of this original definition of variance is this statement. Variance of x can be defined or shown to be difference between expectation of x squared and the expectation of x squared. Not the same thing as its definition, but very closely related. And sometimes much more useful formula than this just the definition. So a lot of people may not remember this formula, the definition of variance, but they still do remember this representation here because it's so useful. So it says that variance of x, first is take the squared x, and then take the expectation and subtract the square value of the original expectation of x. Have to show it why. How do you show it? So this one is the same thing as this. What we are given is only this. So basically you have to start from here, because that's a given definition, and try to reach the other end of it. Do it, you actually do it this way. Here's how. I think it's a blank on your notes, so you might want to write them down if you want to, but if you understand the whole process, you don't have to. So again, mu del is the expectation of x. It's just a short and simple notification. How to justify the first equality? So that's just a variance, the definition of variance. Variance of x is defined to be expectation of x minus its expectation first and then square it. And then you take the expectation of the whole thing. So the first equality is nothing but the definition of this guy. We just introduced one page back. What about the second equality here? How do you move from here to there? So where do we get this? This equality here. How do you justify it? Given that this P of x thing is the probability mass function of x, so it's a PMF of x. That's why there's an x as a subscript. So that's the result of proposition. Yeah, the proposition. So given this proposition, we can conveniently compute this expectation of certain function of x, and that function of x in this case, what this? So that's another function of x, right? Subtract some number from x and then square it. That's a real value function. So expectation of that can be easily sum of all those possible values for those functions, but then you multiply that one by PMF of x, not the PMF of that function. That's nothing but the proposition. So the second equality is ensured to hold by the proposition that we introduced. Another application of the useful and handy proposition. Third one, just expand it. Expand this quadratic. So x minus mu squared. And first square the first term inside. And then there's the interaction term. Multiply the x by negative mu. And then you have to twice it, double it. And then add up the square value for the second entry, which is negative mu. That's the same thing as mu squared. And then finish up by putting this PMF of x. So that's just a simple algebra. The fourth one is the U distributive summation, because first apply this same probability mass function into each one of these three terms inside of bracket, and then break the entire sum into three different sums, partial sums. First, the summation applies to the first term inside, and so the same summation applies to the second one, and again the same operation can be applied to the rest of the stuff inside this big bracket. So end up with these three terms. So the punchline of this proof is actually this second last equality. Once you are done with it, you're okay. Claim that the first summation over x and summand this x squared times the probability mass function of x. Claim that that's the same thing as e of x squared. How do you know it? So you see that the first partial sum here, that's nothing but the expectation of x squared. Where do we pick that up? Proposition again. Yeah. So again, the powerful and handful, not handful, handy, the result that we obtain from that proposition. What about this second equality? Not the second, the second part, second sum. What is it equal to? Huh? Expectation of x. Very nice. Why? What's funny? Nothing funny. So that's e of x. It's just a definition of x. A definition of expectation of x. First, I put that x itself, and then multiply that one by its PMF. So that's e of x. E of x is mu. So you have a twice mu, and then back it up by another mu. So that's nothing but twice mu squared. That's why you have this one down here. What about the last sum? This guy? What is it equal to? 1, because it's a PMF. You sum up all those probabilities taken up by this PMF over all those x's. It must add up to 1, otherwise it's not a valid PMF. The fact that they sum up to 1 just ensures that that's actually valid and a legal PMF. So multiply mu squared by 1, that's still mu squared, so you just put mu squared. But then the last mu squared cancels one of these mu squared before, because the signs are different. So finally you end up with this expectation of x squared and subtract the mu squared, which is squared value of those expectation of x. Done. That's useful formula. Why is it useful? Because pretty much often time, computation of expectation of this messy stuff inside a lot more difficult than just the computing expectation of x squared. Expectation of x, that's nothing. You have to do it anyway, whether you do this way or that way. Because if you stick with the definition, the very first thing that you have to do in figuring out what the value for this variance is, you have to figure out this one first. So that one should be done, whether you follow the first way or the second way, so that it doesn't make any difference. The only difference between whether you should use the second version or the first, which computation is more straightforward between this or that. And clearly this one is easier to compute because you have only one term inside compared to three different terms inside. So computation of the second representation of variance of certain random variable is much easier to follow and understand or do some work with instead of this initial definition of it. So that's why. Second corollary. So under the operation of expectation of certain combination transformation of x, in the linear case, everything goes through. So mean of a linear transformation of certain x is the same thing as the linear transformation of e of x, but then whether the same relationship and result holds true with the variance operation, answer is actually not. There's a slight difference. So it states that the variance of the same linear transformation of x that we just discussed a minute ago, now you should take the variance of it instead of the expectation. This a actually disappears, and then you have to, when you pull this coefficient out, first have to square it and then multiply that one by variance of the original x. So there's a crucial difference between taking the mean expectation of this transformation and then taking variance of the same transformation. So a suddenly disappears and then b gets squared when you pull that one out, and for the following reason. So how do you verify it? Simple, stick with the definition. So starting from the left hand side and try to reach what's on the right, which is this one. So the left hand side is this one, variance of the transformed x, a plus b times x. So stick with the definition of it, definition of variance. First consider the transformation and minus the mean of it. But the expectation of this linear transformation of x, we easily saw from this earlier corollary, go back to the first corollary, expectation of the linear transformation of x is the same linear transformation of this time e of x, not x. So just to adopt this result, copy it, and that's why we have this a minus b times mu, because you have to minus the entire thing. So what's going on is the following, if you somehow don't see it. So what we are having is first this, right? So that's the variance of it. But then you see that the expectation of this linear transformation here, if you apply the first corollary, that's a plus b times e of x, but that e of x is simply replaced by mu, which is the same thing. So you have a plus b times mu, but you have a minus in front of it, so the whole thing becomes negative a and negative b times the mu thing. That's why you're having it. But then the same a's, first you add it and then subtract it. It's the same thing as don't have it all to begin with. And what's remaining is b times x minus b times mu. Same b, so you can factor it out and then square it. So that's why the small b becomes b squared. Then you again square the rest of them, which is x minus mean of x, mu. So kill these two a's because signs are different. You're only left with b times x and b times mu, but there's a minus in front of it. So factor this b out, and then what's remaining is just the x minus mu. Then what about the second last equality? How do you show that this is indeed valid? Argue for that because you feel like it. You have to justify everything step by step. Otherwise, other people jump on you and say that you're wrong. So why do we know that that's the case? Again, because of the corollary. So corollary says this. So initial corollary states expectation of linear transformation of x so special case of that, let a equals 0 b equals b squared looks obvious. Change the b to c because it might confuse you. So that's corollary. And as long as they are constant, you can assume any values. So assume that the first constant a equals to 0, and second c happens to be the same as b squared, and you have that result. Right? So if you actually plug that in, so this one goes away. Oh, wait, something, yeah. So you have a b squared, and a goes away. You only end up with b squared. So that's exactly what we are having. Another application of the first corollary. And last step is just the definition of variance. So you're done. So what's the lesson? Whether you add up or subtract certain constant from the variance operation doesn't change anything. Variance measures how much spread that you're having. So the initial distribution is right here. Variance of x measures how much variation you're having under this distribution. But adding certain constant is basically sliding the entire distribution either to the left or right. By adding it, something like a or some other constant, either to the left or right hand side. But the amount of variation or spread in this distribution stays exactly the same. But if you multiply, of course, you have to double that constant by taking the variance operation. So a doesn't play any role. So some numbers are added or subtracted to this the original process, and then take the expectation. From this picture, you see that it doesn't change anything in terms of its spread or variation inside. So a goes away, but then this remaining b coefficient still plays some role because entire distribution might expand it or shrunk depending on its size. So you have to square it first and then take it out. That in mind, try a few examples on this operation of computational variance. First one, always the first example is of rolling a die. If you roll a die 100 times and toss a coin 100 times, this class is like 2/3 over. Then you have a central limit theorem in the beginning of sum, and that's it. So how do you compute the variance of this when x is defined to be the outcome from rolling a fair die? So with the 6 equally likely outcomes, 1 through 6. Use the definition or use the useful formula, but probably using the useful formula might be easier to compute. First, figure out the mean of it. Did it many different times in the past, so that's 7/2 or 3.5. And what's new is that if you stick with the second representation of variance of x, not its original definition, first have to compute the expectation of x squared. That's this. Again, the application of the proposition. Because this 1/16 is the PMF of the x, not x squared. Those are two different processes. You shouldn't mix them up. Reason why we can easily compute something like this is because of that proposition again. Second equality is just algebra. So what it says is that first figure out the first potential values for this x squared is of course 1 squared times its probability of x equals 1, not x squared equals 1. So that's 1/6. And similarly, you can introduce the second case, which is 2 squared, and equal chances of occurring. So it's another 1/6, and you just repeat until you are done with the last case, which is x equals to 6. If you do the computation correct, it's a 91/6. With that, you go to the useful formula, the computation of variance, e of x squared, and then you subtract the squared value for the expectation of x. But expectation of x is already figured out. It's 7/2. Square that and subtract that value from the initial 91/6. You get the answer of 35 over 12 if everything goes all right. Okay. You can do it the other way. I mean, you can stick with the definition. First compute the mean, and then come up with a deviation of those possible values for x in each case. Square them, sum them up. Again, if the computation goes all right, you still end up with a 35 over 12, but you'll see that quite easily. It's the first way, using the useful formula instead of just sticking with the definition. Makes the entire computation somewhat easier and more straightforward. Okay. Second example. Getting even simpler. Compute the expected value and standard deviation of this x when the probability mass function is the same as this given table. Three possible values, 0, 1, or 2, and then the associating probability for each. 0.2 first and 0.4 for both of 1 and each of 1 and 2. So first compute its expected value and then go for its standard deviation. Same thing as computing variance of it, but the answer itself is different. Numerical value will be different. So since it's a simple case, do it now and then let's compare the answers. So this is section 1, right? So you guys had the first quiz of just switching those sign of the coefficient b thing to plus to minus when you compute the sample standard deviation, right? Your quiz tomorrow will be harder because the first quiz for the second section was harder than yours, to be fair. Is it harder? Is it harder? One was hard and the other was straightforward. I don't know which one it was. It's very confusing because this class meets at 10:30 tomorrow. So if it still meets at 9, it's easy to see for me what section 1 and what section 2. But since you guys come here at 9 one day and then 10:30 another, sometimes it's section 1. I'll make sure. Go back and make sure that you get a hard one. If I assign again the hard second quiz to the second section, people will be mad. So let's see what you come up with. Expectation, it's 1.2. Get the three different products and add them up. First one is still 0, but the second one is a 0.4, and then the third one you come up with 0.8. So sum of them is a 1.2. Finish that one up by just saying equals 1.2. And then given the expectation of x variance, this time you stick with the definition because it's just only three different cases. Subtract the computed mean, which is 1.2, from each three cases. First the 0, 1, and 2. Square those deviations and multiply them by its probabilities, their own probabilities. Then variance turns out to be 0.56, and then you shouldn't forget to take the square root of it in order to transform that into standard deviation. So the final answer for that one should be 0.78. Of course, the exam questions and quizzes will be a lot more thought-provoking than just this simple playing around with those numbers, because it's just too straightforward to be put on those quizzes and exams. So some other more interesting applications, one of them could be this one. So there's a candidates for a certain job, and the number of candidates is this little n, usual notation for sample size. So there's a certain job, they're doing the screening of those candidates. Say that there are n different candidates are competing for the same spot, and that they can be ranked in terms of certain criteria. maybe their exam score, or their in terms of college GPA, or some other criteria can be used to rank them up. So the first guy assigned the rank of number 1, second best guy given the rank of number 2, and third best guy given the rank number 3, and so until the very last end, which is n. So if this random variable x to be defined to be as the rank of the randomly chosen candidates, and x we assume to follow certain following probability mass function, just simply 1 over n. Given this PMF and given this x, you want to compute the expectation first and then variance of it this time. How do you do it? So x is the rank, any number between 1 and n, because there are n different candidates, and probability mass function is just simply 1 over n because they are all equally likely. So the chances that you will get the rank, say 10, so exact the same as the probability that you will get the rank 20, and that's 1 over n because there are n different candidates. So given this value for x, which is your rank, and given this probability mass function PMF, you first want to figure out what's the expected value and what's the variance of it. So first the expectation, what is it? It's simple. The expectation. Anyone did it? So there's a PMF, and values that can be taken by x is just your rank, which is any number between any number 1 through n. So what's the mean? What's the first thing that I have to write if you want to compute the expectation of certain thing? Start with summation. I runs where to where? What's the first value that x can take? 1. All the way up to where? What are these two values? Right. X your rank, and then there's equal probability, which is 1 over n. Here I used I, but it can be any dummy. I put x there, but it's just the index, so it can be I. Answer doesn't change at all. So the value taken by this x is your rank, the integer 1 through 6, not 6, n. And then PMF is given to be 1 over the sample size, which is again n. So that's x times 1 over n thing. But then you see that the 1 over n, the probability mass function is completely free of the index x, so you can pull it outside. And what's remaining inside? Just the x. So you're supposed to add up 1 through n. So that's nothing but n times n plus 1 divided by 2, by the simple sum of those series that you might have learned back in high school. So you must have learned something like this one. Right. Friedrich Gauss figured this one at the age of 10, which is a famous anecdote. adding up positive integers 1 to 100. It just came up with the answer 50-50 in 10 seconds while his teacher was still struggling. So if you, the summarized term is 1 plus n divided by 2. What about its variance? Do the exact same thing, but if you use the useful formula, first go for the expectation of x squared, and then subtract the square value of the mean that we just computed. So why not? First compute the e of x squared, which is this one, and then subtract the square value for those first mean that we just computed. A bit messier than the first case, but still can be doable. By the way, don't worry about those formulas for the quiz. Formulas will be given. If I ask you to work on certain formula, the quiz will state the formula itself. So if I ask you something about Bayes theorem, the quiz starts with the Bayes theorem. It states the theorem first and then asks you questions. So don't try to memorize those formulas. Not to worry. That's the same for the quiz and the exam. And the exam, it's even better because you'll get the formula sheet. So it's a small exam book, like a 10 to 15 pages, stapled. So first front cover is just your name and ID, and then those score sheet. Second page is a bunch of formulas, and then the actual exam starts from page number 3. Actually, I have no excuses. So typical excuses students give me after the exam is, I forgot the formula. There's nothing to forget because you have provided the formulas. It's just all a matter of how you apply and where to apply. But easy definition like a conditional probability, you should know it. I mean, so if I ask you to compute certain probability, if you have to figure out what this one is, it's defined to be P of A and B and divided by P of B. This formula may not be given because it's just way too simple. But other than this, something like a Bayes theorem, something a lot more involving, those formulas will be given. So, but nothing like this because it's just too simple. Right? Last example, I think is the most interesting one. Gambling. What could be more fun than gambling? So origin of all those probability theories is actually gambling. The best probabilists back in the 18th century were the best gamblers. So the situation is you have two options. Either to take the 1 over $3.5 fixed amount of price, or you play gamble. And if you go to the second route, play gamble, there's uncertainty. Your payoff depends on what you will get. So roll a fair die, and then the outcome can be named as X, and your payoff is just simply 1 over X dollar. So if you get 1 after you roll that, your payoff is $1 because 1 over 1 is 1. But if you end up with the biggest number of 6, your payoff goes down by 6 times, 1 over 6. There's a whole lot of uncertainty. Either play or just settle down with this fixed pay of 1 over 3.5. Given choices, you have to make your decision. either go with this safe money, 1/3.5, or go for gamble with the hope that you might end up with actually $1, which is bigger than the fixed amount of 1/3.5. So how do you choose? Go gamble or just go home with that fixed amount of money? Any idea? What did you do? Most people don't care. What do you need to figure out in order to make some best decisions in situations like this one? In case you gamble, what's your payoff? Payoff. How much do you bring home if you play gamble in this case? 6 different outcomes. So if you come up with 1, you go home with the $1. If you come up with 2, you go home with 50 cents. If you come up with 3, you go home with 1/3 of a buck, and so forth. But in the second case, it's 100% certainty. You go home with 1/3.5. Why 1/3.5? I don't know. I just took it from one of the textbooks that I used as an undergrad student. So how do you compare? I mean, scenario 1, you have 60 different outcomes. Scenario 2 is just a fixed one. You still have to make a choice. How do you compare those two? Expectation of what was that? Expectation what? So yeah, we're on the right track. You have to you have to compute expectation of certain thing. But what is that thing? That's the key. So X outcome from rolling a die need to compute expectation of what? Expectation of what? X, yeah, 1/x. That's what I need to do. Just need to figure this one out. So what you bring home, if you actually take the option of playing gamble, is this guy. You have to take the expectation because there's a whole lot of uncertainty. And then if this expected value turns out to be bigger than 1/3.5, you go gamble. Otherwise, you just take the fixed amount of money home. You compute the expectation of this one. You get something like this. Given the summand, which is the value that you're taking the expectation for, which is 1/x, and then probability mass function is just simply 1/6. So 1/6 is just a fixed number, so you can bring it outside, and what's remaining inside the summation is just the value for that payoff, which is 1/x. And if you do the computation correct, so for moving from here to there, that's when you need a calculator. And of course, if you leave everything correct in this form, still get the entire credit. But sometimes, if you have to compare these two different numbers, might be more convenient and useful to come up with those final one numerical value answer. So in that case, you need some tool, like a machine, calculator. So it's a 0.08. Then if you compare that with the fixed amount of price, in case that you don't choose to gamble, that's less than 0.3. So actually in this case, you pay off on average by playing the game, by gambling. End of chapter 5. Questions? Any thoughts or comments that you might want to tell me? Nothing? You understand everything? More or less? The next one is some popular distribution functions. But this one I'm not going to start covering today. It's something that we'll start tomorrow. There are 4 major topics in this chapter, starting with the Bernoulli distribution binomial. By far the most important one out of these 4 is the second one. Will be heavily and extensively used for the midterm exam. Binomial distribution at the top of the list. The other 2, geometric and Poisson, I never used it on the exam myself before. I covered it in class, and a few questions were assigned to this one on homework problem sets. As far as those exams are concerned, I never asked them before. So it's predominantly the first 2, so much more important than the last 2. So if you understand fully, first Bernoulli and binomial especially, then this part is okay. But then if the last 2 are not important, why do we still have to cover them? Because I need to talk about something. If I just talk about binomial and Bernoulli, that's just 1 minute. And plus, in case you take more advanced statistics courses, geometric distribution, Poisson distribution play a major role, especially the level of class difficulty goes up and high. You still have to cover them. So the stuff on these 4 actually start tomorrow, but make sure that you bring this handout. And quiz, again, the schedule to be the assigned the last 15 minutes of tomorrow's class.